Okay, time to get started. So last time we were talking about limits, various different aspects of limits. We talked about the definition. It's not that bad, really, but it's surprisingly delicate. You got to be very careful with the definition of limit. Make sure you don't inadvertently say something that is kind of meaningless. Right? Easy to do when you're talking about limits. So anyway, we talked about the definition. We talked about how you can view limits from the point of view of polar coordinates sometimes. And sometimes that allows you to compute the limit. Again, everything has to line up, everything has to work out, but sometimes useful. Then we talked about this idea of approaching from different directions, or more to the point. We talked about approaching along different curved paths, potentially curved paths. You can never use this argument. Look at all the different paths along which I've approached. You can never use that argument to prove that a limit exists or is a certain value. It just doesn't work because you just can't check all the possible paths. You would have to check all of them. You can't. There's too many. What you can do is use this approach, no pun intended, coming along different curves, right? And if you get different answers along two different curves, then you can conclude that a limit does not exist, right? So that's still a useful method. If you're faced with a question, hey, compute the following limit. Once you realize that it does not exist, you're done. There's no need to look further or study it any further. Okay, all right. Picking up from there, related idea called continuity. I hope you remember the definition of continuity from single variable calculus classes. There's arguably, depending on how you look at it, 3 requirements for a function to be continuous. At a point A, we require that the function be defined there. So f of A has to exist. Secondly, the limit has to exist. And thirdly, those two values have to equal to each other. Okay, so it's the same thing, the equivalent idea in the multivariable context. So we use limits to define continuity. And here's a theorem. If you know a function's continuous, and by the way, this is very important, the function has to be known to be continuous. If the function is known to be continuous, then you can compute limits by this handy-dandy formula. It's you might call it the plug-in formula. Let me zoom for effect. If you want to compute a limit like this, whatever. Whoops. Oh, the thing won't let me. Sorry. Whatever point you're approaching, plug that in to the function whose limit you're computing. That computes the limit for you. Now, not a terribly big surprise because let's again go back and compare this to our definition of the limit. Notice they're the exact same equation here. So this equation, we're using it as a definition of a continuous function, definition of continuity. We're also using it as a method for computing limits. Now, y'all should be very uncomfortable with this. What this is suggesting is that, hey, if you compute a limit, you can decide if a function is continuous. And if you know a function's continuous, then you can use that to compute the limit. Doesn't it seem kind of circular? Therefore pointless? Okay. All right. It would be pointless, except for the fact that previous mathematicians have already proved that a large, very large category of functions are all known already to be continuous, and you don't have to reproduce those proofs. You may cite these 2 great big theorems. These are enormous theorems. Start with this first one here. This says the following types of functions are all continuous where they're defined. I emphasize where they're defined. All polynomials are continuous. You don't have to prove that. You don't have to compute a limit and confirm that you get the right value to deduce that a polynomial is continuous. You just cite polynomials are continuous. Established. Likewise, trig functions. Now we've got to be careful with this one. This, very importantly, I've got to come back to this little clause, where they are defined. Obviously, the tangent function is not continuous everywhere. It doesn't even exist at certain values, right, where you're dividing by 0, the denominator is 0. So we're not saying it's continuous everywhere, but wherever the tangent function is defined, it is continuous. This is true for all 6 of the trig functions. Etc., logarithms, exponentials, rational functions are all continuous where they are defined. Of course, some of them, especially note rational functions, are not defined everywhere. Okay. So yeah, very handy. Now, what if you end up with some function that's not exactly in one of those categories? Like what if you end up with a sum of 2 of those functions, or a product, or a scalar multiple of, or a fraction, etc.? Well, we have another theorem here that says if you have 2 known continuous functions, combining them in any of these ways produces another continuous function. Right? So this is actually pretty powerful. Now I do have to emphasize this little asterisk. If g of a is equal to 0, then we have a divide by 0 problem. That is a big worry. So this the fraction result only applies if the denominator value is non-zero. Okay, so let's apply that idea to this example. We need to compute the following nasty-looking limit. Right? And, well, here's the thing. X squared is a polynomial, continuous. Cite, right? I don't have to prove it, I just cite. X squared is continuous. Z, y cubed, continuous. Right? In fact, this whole numerator is a polynomial, continuous. Okay, let's look at the denominator for a minute. xy, that's a polynomial, continuous. E to the z, that's an exponential, continuous. Now, the sum xy plus e to the z is not a polynomial. It's not an exponential, but it is a sum of 2 known continuous functions. Therefore, this denominator is continuous. Right? So what we have here is a fraction of 2 known continuous functions. Then we cite this result up here about f over g, fractions. Check that the denominator is not equal to 0 at the point in question. This is a continuous function. So we can compute that limit by the plug-in formula. I'm just going to take these values 2, 1, 3 and stick them in there and see what you get. That's the limit. Okay, so continuity is a really powerful tool for computing limits because of the fact that we have this pre-existing information has been done for us. All right, so that's the good news. The good news is it's a very powerful tool and it's very easy to work with. You just literally plug in the numbers. The bad news is it's correspondingly rare that you need to use this result because it's so easy, right? So it doesn't come up super often, but it does come up sometimes. So anyway, be on the lookout for it. I mean, I encourage you, in fact, to one of the first things that you should do when you find a question that says compute the following limit, you should just say, hey, let's slow down. Let's take a minute, just a quick second. Any chance this thing's continuous? Look very carefully at the point, right? It's only at this point that you care. I don't care if it's continuous at the origin or if it's continuous somewhere else, whatever. At the point that you're approaching, hey, maybe it's continuous. If it is, bam, quick solution. Okay. All right. If it's not, which is probably the case, then try something else. Okay. A couple other quick observations I'm going to make about limits. This first one I hope is no surprise. If you are taking a limit of a vector-valued function, now we've been talking about real-valued functions up to this point, and I could modify the definition that we've done already to a new definition of vector-valued limits. And I'm not going to, but you could probably even guess how it would go. It would be highly analogous to what we've already done. But anyway, turns out to be a true and very convenient alternative to say that the limit of a vector-valued function is just the vector of individual component limits. So each one of these component functions, f1 of x, for example, just that first component function, you could just take its limit individually. Ditto the second one, et cetera, and that will compute the correct limit for you. So it's what I'm going to call exactly what you would expect to be true, right? More importantly, it is true. So anyway, it has to get said. And then a second idea I want to talk about is compositions. If you have two known continuous functions, f and g, then the composition is also continuous. So for example, let's look at this guy right here, e to the power of xyz. Now that is not exactly the exponential function. That's not e to the x. Right? It's not a polynomial. And then you might think to yourself, well, okay, yeah, but you could build this out of functions we've already talked about. Isn't this like a product, or it's not a sum, but it's like a product or multiple, or can't you, using the processes that we talked about on the previous page, can't you generate this function? And the answer is practically no. You can't. This is not a product, for example, of known continuous functions. It is, however, a composition of known continuous functions. The polynomial, right? That's a polynomial. It's known to be continuous. And what are you doing with that polynomial? Well, you are then exponentiating. And the act of exponentiation, that is a known continuous function. So by this theorem, we know that this is a continuous function, and again, computing the limit is easy. Okay, so that finishes up 2.7. By the way, for those of you who just came in, I apologize. I forgot to send out the email yesterday about the homework assignment. We did not do enough of 2.7 yesterday for me to want that to be assigned as part of yesterday's homework assignment. So 2.7 will be part of today's homework assignment, which will be due, let's see, today is Thursday, Monday is a holiday, so today's homework assignment is due on Tuesday. Okay. All right. So now, moving on. I'm sorry? I think that's what we talked about before. Can you, those of you who were before? Okay, that sounds right. I owe you an email, though. I'm going to triple check when I get back to my office, and I'll send you an email back. Okay, so we're done with chapter 2. Moving on now to chapter 3. I want to say a couple of quick words about why the section on linear algebra is in here. You might think to yourself, wait a minute, isn't that Math 216 or Math 221 or Math 218 now, by the way? As a side note, if any of y'all are going to be CS majors or stat majors, Math 218 was created exactly for you. It's a linear algebra class for stat and CS majors. So it's something I think you should give very careful consideration to. Engineers, of course, are going to be taking Math 216. And possible math majors, again, come talk to me if you think about want to be a math major, but Math 221 is the right choice for you. Okay, moving along. So why is linear algebra in a multivariable calculus course if it is its own course? And the answer is, it turns out that if you have a little bit of linear algebra, it doesn't take much. If you know just a little bit of linear algebra, then you can use that as a very powerful tool for making a much more sophisticated and powerful presentation of multivariable calculus. It's just really useful to know linear algebra. It doesn't even take much, just a little bit of linear algebra in doing multivariable. So I include a little bit in here. It's only going to take us today, pretty much, to do this, depending on how much I talk, but I'm going to try to keep it to just today. Then you might think to yourself, well, why don't they just switch the order? Why do we do 212 and then 216? Shouldn't they do it in the other direction? There is much discussion about that as a possibility. In fact, the math department quite a few years ago created an honors sequence of linear algebra and multivariable calculus, where linear algebra comes first, for largely this reason, right? And then the multivariable comes after. That's 221, 222. Again, math majors, talk to me if you like. But Math 212 does not have a linear algebra prereq. I can't assume you've had a linear algebra course. In fact, I mostly assume the contrary, right? You've probably had a little bit of high school, like maybe they showed you matrix multiplication or something like that, right? Very teensy-tiny little bits of linear algebra. We're going to need more than that. And so thus, these two sections. Okay, so now this is, of course, fundamentally a multivariable calculus course. We're going to want to talk about derivatives of multivariable functions. Turns out there's lots of ways to talk about derivatives of multivariable functions. It's not like single variable calculus in that sense. In single variable calculus, there's the derivative. That's it. Right? In multivariable calculus, there's various different kinds of derivatives, and they relate to each other in various different ways. And when you add it all up, though, I mean, the most complete way to describe the derivative of a multivariable function, it is an object of linear algebra. It's a thing called a linear transformation. So I need to tell you all what a linear transformation is. Right? I mean, if we're doing calculus, we're going to need to talk about derivatives of multivariable functions. They are linear transformations. We have to know what linear transformations are. Okay. By the way, another little quick tangential, little cultural note. Linear transformations are extremely useful. They're all over the place. I can't digress too much here, but I like to say it as linear algebra and linear transformations are as fundamental to multivariable analysis as Algebra 1 is to single variable analysis. So Algebra 1's a pretty big deal in calculus. Can you imagine trying to do calculus without knowing Algebra 1? This doesn't make any sense, right? It's kooky. Well, linear algebra is that important from a certain point of view in these other things. Okay, so let's dive in. Let me remind you of this notation, right? We've talked about this on the first day of class, a different way to write vectors. Instead of writing v1, comma, v2, comma, v3, we write it as a column. Ends up being useful. We're going to see why today. We've already seen minor reasons why. Quick definition. I'm going to define this thing called a linear combination. This is arguably the fundamental construction of linear algebra. All of linear algebra, from a certain point of view, boils down to thinking about this kind of a construction. So I want to make sure we're clear on what it is. A linear combination says you've got a list of vectors. I'll use green, sure. A list of vectors. And a linear combination says you're going to take those vectors, each one you're going to multiply by some scalar. Now, by the way, that scalar may be 1. That scalar may be 0. Whatever. Right? So you're going to take the vectors in question, you're going to multiply by some scalar, and then you're going to add them up. So it's a sum of scalar multiples of the original list of vectors. You give me a list of vectors, a linear combination is any expression of this form. And I mean, you can see why we call it a combination, because I think you're taking these vectors and you're combining them in this linear way. I mean, the term is pretty natural. Okay. All right. Okay. We're going to study a certain kind of multivariable function. This is just a reminder that if you have a multivariable function, it's a function of several input variables, but this function itself might have several outputs. It might have several components, f1 through fm, and if the function as a whole depends on these several input variables, x1 through xn, that means that each component also might depend on all of those input variables, x1 through xn. So that's just really more of a reminder than anything else. And here's our definition now, definition of a linear transformation. But by the way, I'm not motivating this, I know. I'm just I'm going to write something down. The motivation is we're going to find very soon. It'll be next week, I guess. But still pretty soon we're going to find that this is exactly the object that we need, again, to talk about derivatives. The details to come later. Just take my word for it. And here we go. A linear transformation. Use a different color. A linear transformation. It's a function. Most fundamentally, it's a function. from Rn to Rm. By the way, I'm giving you, this is not the most general definition. This is a Euclidean version of a more general construction that we'll talk about in Math 216. But anyway, so a Euclidean linear transformation. It's a function from Rn to Rm, domain target, that has the following two properties. Let's look at them one at a time. This first property says if you add two input vectors and then plug into this function, you need to make sure that it will always be the case that what you get is, in fact, the sum of the two otherwise individual output vectors. So in other words, you can add before you put into the function, or you can put them into the function and then add the outputs. You should get the same thing either way. So that's our first requirement. Be a pretty handy feature for a function to have. Give me 2 seconds. I'll be right with you. Not all functions have this property, of course, right? But you could kind of imagine, hey, if a function did have that property, nice, right? You can think of all the algebraic, how convenient would that be, right? It's not true for stuff like square root. That's why square roots are hard, algebraically, right? So that's a very desirable feature for a function to have, yes?
Can we have a situation in which we have t of x minus y? Does that become t of x minus t of y?
It is going to, and I'll show you why in just a moment. Yeah. But yeah, so it's a great question. Let me come back to it in like 30 seconds. Okay, so there's two requirements to be a linear transformation. Well, or several, but so it has to be a multivariable function from Rn to Rm. And the two otherwise requirements are, it's got to play nice with vector addition, I like to say. And the second one is it has to play nice with scalar multiplication. So, again, not every function would have this property, but wouldn't it be nice? Wouldn't it be algebraically convenient if a function had the property that whenever you multiply the input by a scalar, that effectively that just multiplies the output by a scalar? Gosh, wouldn't that be nice? Just move scalars in and out of this function anytime you feel like it. That would be a handy feature for a function to have. So let me answer your question now. What happens for a function that satisfies these two properties? What is t of x minus y? Well, using the first property, I can rewrite this as t of x plus t of negative y. Right? And now using the second property, I can rewrite this as t of x. Well, more to the point, let's look at the second term. T of negative y, that negative 1 factor there is a scalar that I can then factor out. So, property 1 gets us to here, property 2 gets us to here, and so the answer to your question is yes, t of a difference is the difference of the t's. Yep.
So for it to be a linear transformation, it needs to be of these forms.
That's right. For a function to be a linear transformation, it has to satisfy both of these properties, non-negotiable, all cases. Yep. Yep. And that would be a really handy function to deal with because it's got these really convenient algebraic properties, and life would be good if we had these properties to work with. And that's, by the way, that's the good news of linear algebra is that you always get to do stuff like this. You always have these two properties to deal with. It's very handy. Okay. Moving along. Now here's a different way to say this. Instead of requiring that a function, my little sloppy terminology is it plays nice with vector addition and it plays nice with scalar multiplication. A different way to phrase that, an equivalent formulation, is that it plays nice with linear combinations. So not just adding, not just scalar multiplying, but if you do any linear combination of inputs, you're effectively going to generate just the corresponding linear combination of the otherwise outputs. And it turns out that these are equivalent conditions. So any function that satisfies those two properties must satisfy this third property, and vice versa. Any function that satisfies that third property must satisfy the first two properties. And that's something that's you can play with on your own if you're interested, or you can ask me in office hours or ask in the help room if you want to see why that's true. It's a matter of kind of you just have to think through the appropriate question to answer and then do the appropriate algebra. Okay, so this is kind of a nice combined, arguably a little bit more succinct way to think about linear transformations. And again, my little sloppy phrasing, a linear transformation is a function that plays nice with linear combinations. Okay, so it's intimately connected to this idea of linear combinations we talked about a minute ago. It's just functions that cooperate nicely, you might say, with linear combinations. And it doesn't matter how many functions are involved in the linear combination, any number of functions. Let me draw the corresponding picture. What's going on here? Here's a couple of vectors, v1 and v2. In the domain, we've got our linear transformation like that. There's our linear transformation T. So two vectors, v1 and v2 in the domain. Those two vectors have images. I don't know what those images are going to be. I don't know, maybe let's say there's T of v1 and there's T of v2. So our requirement is that if you take some combination of v1 and v2, so now let's look at this linear combination here. The way I've got this drawn, this is about, I'm going to say 3/2 v1 plus maybe about 1/2 v2. So this is a linear combination of v1 and v2. If you take a linear combination of v1 and v2 and look at its image, so T of that linear combination, you just need for that image to be the same linear combination of the otherwise images. In other words, whatever linear combination that you're doing in the input, the outputs have to have the exact same linear combination relationship. So this is kind of a picture of what linearity looks like. 3/2 of that plus 1/2 of that gives you the blue input. 3/2 of this plus 1/2 of that gives you the blue output. Everybody see what we're talking about here? Okay. Cool, yeah.
So you can kind of create your own given any two vectors, right?
Well, yeah, that's right. I mean, if you know what T of v1 is, and if you know what T of v2 is, it tells you a tremendous amount of information because, well, this, if I know, actually, we're going to talk about that explicitly. But just to follow up on your thought, yes, if you take any linear combination of two vectors where you know the images, well, you know what those images are. You know that the image of this has got to be just the appropriate linear combination of these images, and so you can compute that image. Absolutely. Yeah. More on that in a few. By the way, a more common terminology, I like to say plays nice with linear combinations. Far more common terminology is it commutes with linear combinations. It's commutes. Y'all know what commutes means, right? Like AB equals BA. Commutes means you can kind of do like that, and it doesn't make any difference. Here, we're not so much commuting things, we're commuting processes, right? Here, it's combination first, then linear transformation. Here, it's linear transformation first, then combination. So the two processes, you can do the two processes in either order, and it doesn't change the value. So thus, it's kind of a, sloppy connection to the word commute, but nevertheless, it gives you the right idea. So people say that all the time. Linear transformations commute with linear combinations. Just to be a little bit less obscure, I like to say it plays nice with linear combinations. Okay. So now everybody's got to go through this tedious process at least once in their lives. This is going to be y'all's. This and at least one on the homework will be y'all's. Yes, you had a question.
Is there choice of C's?
It has to be true for all. No, it has to be all scalars. So it's not enough for this to be satisfied for at least one instance. This has to always be true for all vectors, for all scalars. It has to be just universally true for the function t. Yep. Yep. So it's a big property. I mean, that's a lot of requirements, right? Every possible list of vectors, every possible way that you might combine them, they all have to play nice with the linear combination. Yeah. Okay. Okay, so again, we're a tedious process. Everybody's got to do this at least once. Here is a function from R2 to R3. Is this a linear transformation? Now let's look at the right-hand side, and you'll notice immediately that this right-hand side, there's no cosines in here, right? There's no exponentials. Nothing is being cubed. There's no square roots. You're going to want to say, well, come on, it's linear. Look at every term is linear. Doesn't it immediately follow that the function is linear? Keep in mind we have a definition now of what linear transformation means. Linear transformation means something very precise. So to ask if this is a linear transformation, I am asking, does that property hold? And we have to explicitly check that property holds before we can declare this to be a linear transformation. It's not enough for it to cosmetically look like it should. So this is just a brute force calculation. Suppose we have an a vector x and a vector y. I'm going to consider here an arbitrary linear combination of these vectors x and y, which, by the way, notice I didn't say it. These are arbitrary vectors. I didn't say 1, 2, and 5, 7. These could be any x, any y in the domain. This could be any linear combination of them, and it's my responsibility now to confirm that doing the combination before the function will give me the same result as doing the combination after the function. And you just gotta plug in and brute force confirm that sure enough, it does work. So here's how we do it. It's just details, but there I've just expanded the linear combination. That's ax plus by. Right now, here I'm doing a little bit of chapter 1. I'm just taking ax plus by and multiplying out and finding the individual components of the vector ax plus by. Notice that these individual components are ax1 plus by1 is the first component. ax2 plus by2 is the second component. I want to compute f of a vector of which I know components. So notice that means that I'm going to be plugging in you got to be careful, with the notation. I'm plugging in the yellow expression into the first spot. I'm plugging in the green expression into that second spot, right? And with that in mind, this output becomes that. X1, don't forget, X1 is that business. Right, x2, for the purposes of what we're computing here, x2 is all of this business. So note, all I've really done is evaluate this function f on this new vector ax1 plus by1, comma ax2 plus by2. Just plug it into the function. Okay. Now this is just a little bit of sorting. Now exactly how I go through this sorting process, I have a goal in mind. I know what I'm trying to get, right? I'm trying to get, this jumble of terms up here. I'm trying to get all the x's over to the left because it says right here. I know what I'm trying to get done. Now I want all the x's over to the left. All the factors of a, you'll notice, need to be over to the left. Likewise, all the b's. All the y's need to be over here on the right, so I just kind of shifted them around. No tricky curves there. That's just shuffling. And as required, that is indeed f of the x vector, and this is indeed f of the y vector. So it's just brute force, right? So just plug and chug. We have confirmed that when you put a linear combination in, you get the corresponding linear combination out. Everybody see how the details worked out there? Okay. Yeah, I think I remember correctly that on the homework you're going to have to do at least one of those, and you just got to do it, right? Okay. Don't just go around assuming everything's a linear transformation. It's not true, right? Here's an easy counterexample. That function is not a linear transformation. Now, conveniently, it also does not look like a linear transformation, right? But that's, we got to be careful. Don't just go around assuming that cosmetics give away the game. Sometimes they don't. But the thing that makes this not look like a linear transformation is the fact that something's being squared. And we know that when stuff gets squared, nonlinear stuff happens. And so this counterexample that I've found, right, here's an explicit counterexample to the linearity requirement. If this function were going to be linear, g of a linear combination would need to be that same linear combination of the corresponding g's. Right? This would need to be true. Plug the numbers in, clearly failed. Right? So this does not satisfy the linearity requirement. Therefore, this is not a linear transformation. Yeah? Everybody see the thing there? So I think I left a dangling thought. Let me go back and complete that. Where did I come up with this counterexample? Well, I was motivated by looking at the fact that here's the part that's the nonlinear part. So let's put numbers into x1, because I know sort of x1 is where that's gonna experience the nonlinearity of this function, the squaring, namely. So that's why I put a non-zero number in the x1 in the counterexample that I was hoping for, and of course it works. Okay. Yeah. Oh, it's just arithmetic. So if you take that linear combination, compute it as a vector, that gives you 2, 0.
Okay, yeah.
Plug it in, turns into 12, 0. Yep. Another little quick fact, it turns out that for any linear transformation, t of 0 is equal to the 0 vector. We don't have to require this. This is, in fact, a consequence of the linearity condition. This is a very handy fact. Every linear transformation, any function that plays nice with linear combinations, in other words, every linear transformation, 0 goes to 0. Every time, no exceptions. So easy to prove this fact. Here is a special case of the linearity conditions, right? Scalar multiples factor out. Let's just let that scalar multiple be 0. Free country. Right? T of 0x has to be 0 times t of x. That's just an immediate consequence of linearity. And notice, of course, that means that we get t of 0 on the left. And we get 0 on the right. Could not be slicker. Yeah? Everybody good? Okay, I hope everybody remembers the standard basis vectors. We talked about these again on the first day of class, or first or second, very, very early in the class. These are vectors these are unit vectors that point along axes. Right? These are the standard basis vectors in R3. Of course, there's also standard basis vectors in any Euclidean space. Anyway, we're going to talk about the ones in R3. These are they. Recall this notation, E1, E2, E3. Okay. It turns out that this theorem here represents a powerful way that standard basis vectors relate to linear transformations. It's a little bit unexpected. It's almost like a magic trick. Suppose you've got some linear transformation. There's an ambiguous statement. Any linear transformation from Rn to Rm. Why, gosh, there's lots of them. Any linear transformation. What this theorem says is that if you know the images of the standard basis vectors, so images of the standard basis vectors, I'm going to write that as T of EI. Keep in mind the EI, those are the standard basis vectors. T of that means we're looking at what comes out, so there's that image. So T of EI is the image of the ith standard basis vector. If you know these images of the standard basis vectors, if you know those, you're done. You know everything. You know the value of T for any other vector. And you might think to yourself, come on, how's this possible? In single variable calculus, and let me draw a axis system here, Calc 1. Suppose you have a function. Is it true that if you know the value of the function there, and if you know the value of the function there, and if you know the value of the functions there, let's say, you know the value of the function at a short list of inputs, does that just automatically allow you to compute the function everywhere else? No, of course not. The function could be all kinds of wiggly in between these two. Right? It just doesn't, there's no clear suggestion of how that could possibly work. That's morally kind of what we're saying here. If you know a couple of values, if you know just the values of the function just at the standard basis vectors, I'm asserting you know everything about the linear transformation. And the proof is very short. 2 important steps. First, recall every vector can be written as a linear combination of the standard basis vectors in a very convenient way. Right? If a vector has certain coordinates, x1 through xn, there's an exercise in section 1.1, I think it was. Every vector with known coordinates x1 through xn is that linear combination of the standard basis vectors. Step 1. Step 2, cite the linearity. That's all that is. Linear combination in, linear combination out. Just using linearity. And now, declare victory. Oh, you want to know the value of T of some vector? Okay, well, we already know all of these. I know T of E1, T of E2, etc. So whatever vector you've chosen, whatever this x1 through xn is, use those as your coefficients. Take that linear combination of the images of the standard basis vectors, and you just computed T of x. Very, very surprising that this goes through. So what this says is standard basis vectors serve a really nice property that if you know the images of those, you know everything there is to know about the linear transformation. All right, we're going to do a lot with this in this course.
Sorry.
Yeah.
Is there anything different between what you're doing there with E1s and like just a constant in linear transformation?
Did you mean the X ones?
Or yeah, with the X1.
Yeah. So these are right. So these are we've got this vector X, presumably a constant. This is a given vector that we want to know what its image is. So yeah, it's got coordinates, and those coordinates are just numbers. So yeah, this is literally a linear combination. The x1 through xn are constants, and so just yep. Right. Anybody else? Okay. So I kind of equate this to a card trick. Like, imagine the following card trick. Somebody takes a deck of cards, right? I give them to you. You shuffle them. Anyone who's suspicious that we might be in cahoots is also allowed to shuffle them, right? And then I say, okay, tell me the top 3 cards. And she shows me the top 3 cards. And then I list all the rest of the cards in order. Wouldn't that be amazing? That'd be a heck of a card trick, wouldn't it? Okay. That's kind of what this is. Okay, tell me just a couple of values of the function. Okay, now I know all the other values. Shocking result. Okay. Here's a picture kind of what's happening there. So keep in mind we've got these vectors E1 and E2. Here I'm, by the way, just for picture purposes, drawing a linear transformation from R2 to R2. So you see 2-dimensional domain, 2-dimensional target. The picture is morally equivalent in higher dimensions. It's just harder to draw. So let's do the 2-dimensional. So there's the inputs, there's the outputs. And the assertion is that if you know these green vectors, then you're good to go. You know what the linear transformation does everywhere else. And the argument is just linearity. that vector, any other vector, well, it's a known linear combination of E1 and E2. Its output then must be the same known linear combination of T of E1 and T of E2, and that gives you its image. That's all that's going on here in that proof. We wrote the proof algebraically. This is kind of the picture, associated picture. Okay. Alrighty. Here's a different way to think about linear transformations. I'm not going to prove this assertion here, but this is not terribly hard to prove. Linear transformations deform the domain in a uniform way, a uniform linear way. Okay, so here's what I mean by that. There's a couple of different things, a couple of different interpretations you can take of that. One is, if you take two parallel lines in the domain, their images should be, and let me put an asterisk on this, should be parallel lines in the target. Excuse me, the only little asterisk I have to put is it might be that the linear transformation actually deforms these lines by compressing them down to just points, so the images might not be lines, but they'll never be curves. Straight lines by linear transformations will always be, at best, at most, straight lines. So the linearity comes across as parallel goes to parallel, which is a nice feature. And you can see that happening all across this little, this little sample picture that I drew here. All these lines are parallel, and their images, you note, all parallel. It's not hard to prove this, by the way. Not hard to prove that if you have parallel input lines, then the image output lines have to be parallel as well. You might even give it a try. Think about, how would you write down algebraically that these lines are parallel? They have the same direction vector, v. Like this one might be x0 plus tv. That one might be x1 plus tv. Different base points, but they all have the same vector. Write down the parameterizations, plug into t, and use linearity. What you will find if you have parallel output line parameterizations. Different way to think about it is if you were to look at a certain part of the domain here, let's say that little part there, and let's ask, I want to focus my attention on that little part of the domain and look at what does its image look like. Well, the image is that little part of the target, right? So this little bit of the domain became this little part of the target. What happened there? Well, it got rotated, but it also got kind of sheared, stretched in a different way, if you want to think about it like that. But there's a certain kind of a deformation that happened there, and with that in mind, what I mean by the uniformity of the deformation is that if you instead ask, what happened to that little bit of space? Well, the exact same thing, right? So however it is that any one bit of space gets deformed, other bits of the domain have to get deformed in exactly the same way. I mean, they might be put in different places, obviously, but the way they get stretched or magnified or sheared or whatever will be the same. Okay, so that's geometrically how you think about linear transformations. Some example. Here's one. This is just I'm just kind of showing off this is about images of standard basis vectors. Suppose you have a linear transformation R2 to R3. So notice domain is R2. Target is R3. And suppose that you know that E1 has as its image the vector 1, 2, 1. Forgive my attempt to draw the vector 1, 2, 1. I put these little dotted lines in there as kind of so that's 1, that's 2, that's 1. The dotted lines kind of help you see perspective on that. So I know that E1 goes to 1, 2, 1, and suppose I know that E2 goes to -1, -1, 3. So there's two little pieces of information that I have about this linear transformation. And question, what else can I conclude about the linear transformation? Well, the answer is I know everything that there is to know about the linear transformation. If you look at the following combination, if you look at the sum of E1 and E2, the image is going to be the sum of T of E1 and T of E2. If you look at some linear combination, like how about 2E1 plus E2? Well, the image is going to be 2T of E1 plus T of E2. Whatever linear combination you take of E1 and E2, you're just going to do the same linear combination of T of E1 and T of E2 to get the output. And so I appeal to your sense of geometry. Well, everything in all of the domain is some linear combination of E1 and E2, and therefore the outputs are all going to be some linear combination of E1 and E2. They're going to be in this plane that's defined by these two direction vectors, T of E1 and T of E2. Correspondingly. Okay. Neat example with rotations. Oh my gosh, time flies. Neat example with rotations. Let me just skip down to the more interesting one here, time being a factor. So let's talk about rotation by an angle theta in R2. So I'm going to come down to where I have a picture of it. Let's see, where do I have better now? Yeah, here we go. So here's a picture of a rotation in R2. You can see we've got E1, and it rotates, become T of E1. And you can talk about E2. There's E2, and it rotates T of E2, right? Or some arbitrary vector. Maybe I have some vector X, right? It's going to rotate by that same angle to give me T of X. Rotation. So I claim that this is a linear transformation. Let me come back up to this picture here, a better picture for this purpose. The act of rotating, it doesn't feel linear because, when you rotate, if you think about it, it's like, isn't there a kind of a curving when you do a rotation? Well, that process, you experience it in a way that's kind of curving, but nothing actually gets curved. If I were to take a rectangle and rotate it, straight lines are still straight lines. Parallel lines are still parallel lines. The way that this little region of space gets deformed, namely it gets rotated by some amount, is exactly the same way that this region of space gets deformed. It gets rotated. They end up in different places, but there is a uniformity to the deformation. Parallel stays parallel, right? It's a linear transformation, and to be a little bit more precise, think about any linear combination. Like here we have, for example, that is a linear combination of these two vectors. When you rotate that picture, now the picture I've drawn here is a 90-degree rotation. It doesn't really matter. But take this linear combination here. If you do a 90-degree rotation of it, it becomes that picture. And notice that when I did the linear combination here, having rotated it, I get the exact same linear combination of the individually rotated vectors. So whether you rotate before you do the linear combination, or whether you do the combination before you rotate, either way, same result. This is a linear transformation. Okay. All right. So, knowing that it's a linear transformation, the previous theorem allows us to conclude that, hey, linear transformations, if I can find images of standard basis vectors, E1 and E2, let me color those differently. You can tell me the images of the standard basis vectors. What is the rotation of E1? What is the rotation of E2? If I know these vectors, I know everything about rotations at that point. Everything else will be determined just by linear combinations. And these two calculations are pretty straightforward. How do you rotate E1? How do you rotate E2? Well, again, here's the picture. There's a rotation of E1. That distance was 1. That means that distance is 1. That means that I have here a right triangle. And so these are cosines and sines. Right? Likewise, if you want to rotate E2, E2 has length 1. When you rotate, the rotation has length 1. So I have here a little right triangle, and the coordinates of t of E2, the rotations of E2 it's going to be sines and cosines, and think about what the appropriate angle is, and plus and minus and all that stuff. And what you end up with, easy trig calculation is these. The rotations are that and that, and then you use linearity to combine. And here's your general formula for how to rotate any vector in R2 by any angle theta. It's really a pretty surprising result. I mean, it sounds like think about back to trig class in high school, and they give you some vector at some random angle that's not known. You have like a 3, 7. 3, 7. You want to rotate that 42 degrees. How would you find that? You'd have a tilted isosceles triangle. It's hard to see how you'd even do that geometry, right? Innocent observation that this is a linear transformation, invoke linearity, bam, we have a formula. Very powerful. Okay. All right. Okay. Moving on to the next, there's a few other examples I encourage you to take a look at that I'm skipping over. Next section is about matrices. I know many of y'all have seen matrices in the past. I don't know how they were necessarily presented to you. They might have just been presented to you as, well, a matrix it's just an array of numbers. And that's fine. It is an array of numbers, but I want to give you a motivation for the arguably more fundamental question. Why would I want to write down an array of numbers? Why? Why are we doing this? Other than it's just an arbitrary, look, this is just what people like to do, right? So why would we, in fact, want to write down an array of numbers? And having written down arrays of numbers, y'all, again, some of y'all have probably seen the formula for how to multiply two matrices. Show of hands, curious? Seen how to multiply matrices? Oh, not that many? Okay, all right, but several. Why is that the formula? What's the reason? Is that natural in any way? I strongly suspect that those of you who have seen the formula for matrix multiplication probably thought it was pretty weird the first time you saw it. I certainly did. So what's with the weird formula, man, right? I mean, shouldn't there be can someone please tell me why this weird formula is what it is? So hopefully I'm going to be able to answer those questions for you. So here we go. Oh, by the way, step 1, please momentarily forget everything that you already know about matrices and matrix multiplication. Just forget it temporarily. And I hope that comes as a relief to those of you who have not seen it before. You don't need to know it. I want to scratch all that and build it all up anew. So here we go. Reminder. We have these ideas called linear transformations. Here's one. Right? We explicitly proved that this was a linear transformation. We also can quickly write down T of E1 and T of E2 and recall that once you know the images of the standard basis vectors, these are they in this case. once you know the images of standard basis vectors, you know everything that there is to know about the function. So, knowing that your function has these images for the standard basis vectors, and knowing that it is linear, then you can just play linear combination games and you can compute any value of the function you want. So really, this information about, you know, how do you compute t is no more thorough than this is, right? You can do anything you can do with this, you can do with this. Yeah? So, said differently, this is an alternative way to write t. I can tell you what t is by saying, here are the two standard basis vector images, and by the way, it's linear. I might as well have given you an actual formula. So let's say fooey on that momentarily, and we can alternatively take this. And the only thing that's wrong with this is, well, it's a little clunky. I mean, you know, there's a lot more ink inside of here than there is inside of there. It's a little bit bigger on the page, so that's uncomfortable. So the way we get around that is just with a choice of notation. So I'm going to use this situation here to motivate the definition of a matrix. A matrix is just a shorthand representation of this point of view on what a linear transformation is. Note, all I have to tell you, if I want to tell you what a linear transformation is, I just have to tell you what are these images, and I have to note that it's linear. As long as it's implicit that, well, of course, the first one that I tell you, obviously that's t of e1, so don't make me, I'm just going to say the first vector I give you will be t of e1. Right? I'm going to tell you the images in order, and likewise, the second vector that I give you will be t of e2. And by the way, of course it's understood that the linearity condition is satisfied because, well, I've already told you it's a linear transformation, so I don't have to state that again. All I really need to do then is tell you what are these two images. And we do it by just making those the columns of this array of numbers, namely a matrix. So this is how you should think of a matrix in math. In this course, Math 212, a matrix is just a shorthand telling you what the images of the standard basis vectors are. But let me say that a little bit differently. A matrix is a shorthand for what is in fact a complete description of the linear transformation itself. Let's say it one more time. A matrix is just a shorthand for a linear transformation. Right? So if you were to see, and this is the definition I'm going to make here, a matrix, the columns are the images of the standard basis vectors. That's simply a way of representing the linear transformation. So we call this the matrix that's representing the transformation T. Let me give you an example, a couple of examples. Here's one. There's a linear transformation. Suppose I want to represent this linear transformation in the shorthand. Well, I need to enumerate what the images of the standard basis vectors are. So I'm going to take E1, plug it in. I get 2, 1. I'm going to take E2, plug it in. I get 0, 3, etc., etc. I take these I take these output vectors. I make them the columns of my array, and that is the matrix. So the shorthand, the matrix shorthand for that linear transformation is that matrix. And you can turn this around the other way, by the way. Suppose you see a matrix. What are you supposed to do with a matrix? What does the matrix represent? Well, it's just, look, we know our definition in this course, what is a matrix is this is a shorthand representing a linear transformation. These columns are just telling you, so 1, 2, 3. Those columns are just telling you the images of, E1, E2, E3, respectively, of course, right, in that order. And so how does that help you deduce the linear transformation? Well, we know that we can compute the value of the linear transformation with the linearity property, right? Whatever your x is, take the corresponding linear combination, and out comes a formula for t of x. Right? So you give me a linear transformation, I could write a matrix, and vice versa. You give me a matrix, you can reassemble the corresponding linear transformation. Okay, so that's what a matrix is. That's why we're interested in writing down matrices. We're interested in writing down matrices because we were already interested in linear transformations. We know these are interesting objects. This is just a real convenient way of talking about these existing, very interesting objects. Okay, how do you multiply a matrix times a vector? Again, I think a lot of y'all have probably seen that before. You may have thought, okay, arbitrary, weird, why do you do that? What's the point? Right? And I think I'm going to be able to give you a very satisfying answer as to why that's the formula. Here's the idea. Keep in mind, whenever you make a definition, you're making a choice. Right? If I want to define what it means to multiply a times x, I need to first decide, what do I want to choose? In what way would this be natural? What's a reasonable choice to make if I'm going to multiply a matrix times a vector? And you just got to go back to first principles and say, well, wait a second, what are these things? What do these represent? How should they interact? Right? And then go from there. Well, don't forget what a matrix is. This matrix A is just a shorthand. By itself, it's just numbers, right? But this is supposed to be thought of as representing a linear transformation T. So, into the question of what does a matrix do to a vector, I've modestly proposed that, well, it should do whatever the linear transformation that it represents does to the vector. What could be more natural than that? A is just a shorthand representing T, so AX should be T of X. Right, now, that's a little bit awkward if you think about it. What this says is, okay, well, if you want to multiply a matrix times a vector, oh man, what we're going to have to do here, now stay with me, we're going to have to take that matrix, we're going to have to figure out what transformation does it represent. See the previous page, right? We're going to have to write down what that linear transformation is. Then we're going to have to take this vector here, x, we're going to have to plug it in to that linear transformation, and whatever we get out, that's going to be our choice of what to call AX. And it seems like a tedious process. Deduce an entire linear transformation, plug that vector in, compute, and then interpret that as the product. And it can be a little, it's not that bad. You can see on the previous page it's doable. But there's a much more efficient and effective way to do it that comes straight out of that comes straight out of this motivation. So we just talked through this. Matrix vector product is as it should be. What does T do to the vector? Okay, so a much more efficient way to do this. Now remember, we've got this matrix here. The matrix, now I know what the columns are. These columns are the images of the standard basis vectors, but I don't want to have to go back and make reference to the linear transformation. In some sense, what I'm already a little unhappy about is that I don't want to have to deduce T, right? I'm kind of trying to avoid T. I want to execute this, but just without ever actually writing down what T is. So rather than call these T of E1 through T of En, let me just call them A1 through AN. We've got a matrix. It's got columns. I'm just going to label them A1 through AN. Very convenient. Okay. And now let's go through this process and just see how it works out. It's very convenient and straightforward. I need to compute T of X. If I'm interested in AX, I need to compute T of X. Linearity tells me that T of x is this linear combination of the images of the standard basis vectors. We've written that down several times. This is just our usual, break out the linear combination, the outside. Well, we just got through deciding that the columns, the images of the standard basis vectors, we just got through deciding that we're going to call those A1 through AN. And so look what we've ended up with. We have here an explicit formula for how to multiply a matrix times a vector. That's just right there. If you want to multiply it's very handy. If you want to multiply a matrix times a vector, you're going to take a linear combination. You can see it right here. It's a linear combination of these A vectors. And what are those? Well, don't forget the A vectors are the column vectors. So when you multiply a matrix times a vector, you're taking a linear combination of the columns of the matrix A. Note in this formula here, there's no reference to T. I don't have to work back and figure out, well, what is the linear transformation T, and then plug in certain things. No, straight from the matrix A. Just take the columns. Okay. All right. So that gives us a handy formula here. This is going to be our definition of matrix vector multiplication. I'm going to multiply a matrix times a vector. Use the coordinates of the vector to take a linear combination of the column vectors of the matrix. The vector gives you the coefficients in the linear combination. The columns of the matrix are the vectors in the linear combination. Everybody see the process there? Very mechanical, very straightforward. Okay. Now, this is not the formula that you saw in high school. I'll bet dollars to donuts you saw something involving dot products. Everybody remembers the dot product formula for computing matrix vector products? Where does that come from? Why is this not that formula? Turns out this is equivalent to that formula, and it's just a matter of writing it down that this works out. So let me go through and sort of let me try to persuade you, for example, that the formula for the first coordinate here is in fact this dot product. That you take the row of the matrix and the vector x and do their dot product to get that first coordinate. So here's the argument. I know I'm taking linear combinations. I'm going to try to use colors to represent the linear combination in a sort of a different coordinated way here. So x1, a1. I'm going to multiply that times that. And then let's see, we're going to have x2, a2. That's going to be a term there that I didn't write down. And then et cetera, et cetera. Finally, we're going to have xn times an. Right, so yellow times yellow plus green times green plus blue times blue. Okay, fine. But now I'm only interested in the first coordinate of this linear combination. Well, the first coordinate of this linear combination is going to come from looking at the first coordinates of the vectors that I'm combining. Okay? So let's see here. The first coordinate of these three individual vectors, just for color coding purposes, I'm going to fill those in. If I'm only interested in the first coordinates, only interested in the first coordinates, what do we have here now? Well, we have this times, just that number there, this times that, and this times that. And note that's exactly this dot product. Right? So it is the same formula. It's just written in a different way. So on the one hand, you can think of matrix vector multiplication as a statement about linear combinations of column vectors. Alternatively, you can think of the coordinates of the coordinates of the product as being themselves individually dot products with the row vectors. Different way to go. Now, I have a strong suspicion Certainly those who have seen this formula in high school might be thinking, you know what, I'm just going to stick with this formula. This has done me well. I mean, it's just, I already know the mechanics of how to do this. I have to warn you, it turns out that that's actually not good enough. Simply, you cannot just decide, oh, I'm just always going to compute my matrix products this way. I'm going to always compute them as dot products. And here's why. All you've probably ever needed to do up to now with matrix vector multiplication is the arithmetic, right? All you've ever you've been given, here's a matrix, here's a vector, multiply them, and it's just do the arithmetic, right? For arithmetic purposes, yeah, this is the best formula. I think this is probably my favorite for arithmetic purposes. We're not just going to be doing arithmetic, right? We're going to be trying to understand how do various ideas connect to various other ideas, and it turns out that what matrix vector multiplication, how that relates to dot products is useful in some ways, arithmetic being one of them. But how matrix vector multiplication relates to linear combinations is really more useful. And certainly it's useful in ways that this isn't. Right? This point of view, this dot product point of view on matrix vector multiplication does not shed any light at all on some situations where this is just perfect. This is exactly what you need. And some of these situations where we need this point of view on matrix vector multiplication, some of those situations are going to show up in this course in significant ways. So please, again, don't just hang your hat on this one point of view and fool you on everything else. I mean, it's nice to understand this, but it's really more important to understand that. Okay, and a couple of quick arithmetic examples. Here's an example. If you want to multiply this matrix times this vector, well, we take 1 times the first column. So first coefficient times first column, second coefficient times second column, third coefficient times third column, and multiply and add it up, and you get that product. Now let me do the exact same arithmetic here. Here I did it as linear combinations of columns. Now I'm going to do the exact same question from a dot product point of view. So this dot with the vector, let's see, how am I going to do this? All three of the coordinates are dot products. Here, let me do this I'm going to use gray for that vector. We're dotting with the vector 1, 2, 3 for all of these. The first one gives you the first one. The second one, second row, dot the gray vector gives you the second one, and the third one, dot the 1, 2, 3 gives you the third coordinate. So again, this is the one that's arithmetically more familiar. You've seen this done before. This might, look more natural. It's easier to do this arithmetic in your head, which is true, right? But give yourself the practice and make sure that you can do this way, because this is going to have important uses in this course. Sorry, I went a couple minutes over time. So we didn't quite make it through the matrix section. Oh well. We'll finish that on tomorrow. Okay. Yeah. See y'all later.